Hi friends, we have already studied DC analysis of BJT. Now in this lecture we will study response of a BJT when an AC signal is applied to its input. And after studying that, we will study amplifier circuits. So to start with, we have already done many questions when a DC signal is applied to a BJT. Now for a BJT, we'll give it an AC signal as an input. Here we will have VCC. Let's say there is no emitter resistance. This is an NPN transistor, and let's say at this point we are taking output. This is input. Beta is equal to 50. Let's say input is 5.7 sine omega t volt. In this question, let's say we have to draw the graph of output versus time, and here resistance is VCC is 30 volt and RC is equal to 1 kilo. So let's say in this question we have to draw the graph of output voltage versus time. We have graph of input voltage versus time. You can easily draw it. Okay, so to solve this, first what we will do, let us first draw the graph of input versus time. This is the graph of input versus time. Maximum voltage is 5.7 volt, minimum is minus 5.7 volt. Okay, so to solve this, let us take it as V input. So first we will find out the condition when the transistor will be out of cutoff region. So for transistor to operate in out of cutoff region, its open circuit voltage at, we have studied that VBE open circuited must be greater than 0.7 volt. So when you will open circuit it, what will be this voltage? Let's say this voltage is VOC, and if you will move from here you will have gain of input voltage. Since this is open circuited, no current can flow here, so there is no voltage drop, minus VOC equal to 0. So VOC is nothing but V input. So we will say when V input is greater than 0.7 volt, the transistor will be out of cutoff region. Okay, so when it is greater than 0.7 volt, this is 5.7, let's say this is the line for, let's say this is the line for 0.7 volt. Okay, so in this region only, this transistor will be out of cutoff region. In one cycle, this is the duration for which the transistor will be out of cutoff region. Otherwise, transistor will be in cutoff region. Okay, so let us first find out the output voltage when the transistor is in cutoff region. Let's say when V input is less than 0.7 volt, then transistor is in cutoff region. Okay, then what will be the output voltage? When it is in cutoff region, there is no IE will be 0. If IE is 0, IB and IC will be 0. So if there is no current here, there will be no voltage drop. So if this is at 30 volt, this will also be at 30 volt. So the output will be 30 volt. Okay, so let's say this is graph of output voltage. So only in this region the transistor will be out of cutoff region. In the remaining part, the transistor is in cutoff region. So in this region, transistor is in cutoff region. Let's say this is 30 volt. Okay, so here you will get 30 volt, and this is dotted line, this is not graph, and after this point again we will get 30 volt. This is 30 volt. Okay, now in this region the transistor is out of cutoff region. So let us try to find out the output voltage in this region. Now here the transistor may operate in active region as well as in saturation region, so that we also need to check. So let us, now it is out of cutoff region, so it will act as a battery of 0.7 volt. So first we will find out IB. To find out IB, we will first move in this loop. We are assuming that the transistor is in active region. So in active region, IC equal to beta IB is valid. In saturation region, this formula is not valid. So first I am assuming it is in active region. So in this loop, we will first find out IB. Here we will have gain of V input minus 25 into IB. This is in kilo ohm, so we will take IB in milliampere to make it a unit of volt. Minus, here we will have drop of 0.7 volt equal to 0. So IB will be V input minus 0.7 divided by 25 milliampere. IC will be beta into IB, and beta is 50. So this will be, if you multiply it by 50, you will get 2 into V input minus 0.7 milliampere. Okay, since we have assumed it in active region, so for active region VCE must be greater than 0. Okay, if VCE saturation for active region, VCE must be greater than VCE saturation. Okay, and I have assumed that VCE saturation is 0. Now what will be VCE? In this loop, from this loop we will find out VCE. Let's say this voltage is VCE. So if you will move from 0 to this 30 volt, you will have a gain of 30 volt. Now if you will move from here, this is IC, and IC is this 2 into V input minus 0.7 into 1 kilo ohm. Since IC is in milliampere, you are multiplying with kilo ohm. This will give you a unit of volt. Minus VCE equal to 0. So VCE will be 30 minus 2 into V input minus 0.7. Okay, so for this transistor to operate in active region, this voltage must be greater than 0. So we will say V input minus 0.7 must be less than 15 volt, and V input must be less than 15.7 volt. So what is the V input? V input is 5.7 volt. V input is always less than V input is always less than 15.7 volt. So this will always operate in active region. So when it will operate in active region, what will be the output voltage? Output voltage will be 30 minus this voltage drop. Okay, output voltage will be 30 minus, what is this voltage drop? Or output is nothing but VCE only. Okay, so what is VCE? VCE is 30 minus output voltage is nothing but VCE. This is equal to 30 minus 2 into V input minus 0.7. This will be 31.4 minus 2V input. Okay, so now you have to plot the graph of this. And when this formula will be valid? When transistor is in active region, or for transistor to operate in active region, V input must be greater than 0.7 volt. So we will start from V input equal to 0.7 volt. So at this point we have V input equal to 0.7 volt. So output will be 31.4 minus 2 into 0.7. Okay, this will be 30 volt only. So there will be no jump at this point. Okay, when V input is 5.7 volt, what will be output? 31.4 minus 2 into 5.7. This will give you 20 volt. This is 30 volt. Let's say this is the line for 20 volt. So you will be at this point. Okay, and this is expression of output voltage, and since input is sinusoidal, okay, so the curve will be like sinusoidal, although we are subtracting it. So you will get this type of graph. This is the graph of output voltage. Since the input is periodic, so now this graph of output voltage will be repeated. Okay, so in this question we have a graph of input voltage, and we first found out the boundary for which it will operate in cutoff region and active region, and for both the regions we found out the expression of output voltage. In cutoff region the output voltage is constant at 30 volt, and in active region we have this expression for output voltage, and this way we plotted the graph. Here we have graph of output voltage. There is one more graph that is called transfer characteristic. In diode circuit, when we studied Clipper circuit, we have already plotted many transfer characteristic. So in transfer characteristic, what we do, instead of drawing graph between input voltage and time and output voltage and time, we draw the graph of output voltage versus input voltage. On y-axis we have output voltage, here we have output voltage, and this is input voltage. Although we are doing a numerical, but this will make a base for you to study amplifier circuits. Okay, so we have two types of expressions. First, when V input is less than 0.7 volt, it operates in cutoff region. Okay, and output voltage is constant at 30 volt. The second is, what was the expression for the transistor to operate in active region? The expression was VCE is equal to 31.4 minus 2V input, and when it is greater than 0 volt, transistor will operate in active region. So from here we found out that V input must be less than 15.7 volt. Okay, if V input is less than 15.7 volt, the transistor will operate in active region. So we will say, but first, to operate in active region it must be out of cutoff region. So we will say, if V input is greater than 0.7 volt and less than 15.7 volt, this will operate in active region. And in active region, what is output voltage? The output voltage is 31.4 minus 2V input. What I am doing here, I am first finding out the condition, an expression for each region. Okay, basically I'm finding out the boundary. This is the boundary for active region, this is the boundary for cutoff region, and in each region I'm trying to find out relationship between output voltage and input voltage, because we have to plot the transfer characteristic. So if input voltage lies in this range, the relationship between output voltage and input voltage will be given by this expression. Now what if input voltage is greater than 15.7 volt? If this condition lies, it means it will neither be in cutoff region nor in active region, so it will be in saturation region. So now we have to get the expression of output voltage when the transistor will operate in saturation region. So in saturation region, what will be the value of VCE? VCE is 0. Okay, and if you see this circuit, output voltage is nothing but VCE. This is C and this is E, and you have to take output at collector with respect to ground, and E is grounded. So in saturation region, VCE is equal to 0. It means output voltage will be 0. So if V input is greater than 15.7 volt, output will be 0. So we have three boundaries. One is V input is less than 0.7 volt. Let's say this is 0.7 volt. The other one is 15.7 volt. Let's say this is 15.7 volt. This is 0.7 volt of input voltage. So in this region, it will operate in cutoff region. Okay, so in cutoff region, what is output voltage? Output voltage is constant at 30 volt. In cutoff region, no current will flow from here, so there will be no voltage drop, so the output voltage will be 30 volt. So we'll say if input voltage is less than 0.7 volt, output will be constant at 30 volt. Okay, in active region, what is the formula? This is formula in active region. Okay, when you will put input equal to 0.7, output will be 30 volt. So you will start from this point only. If you will put, obviously this graph will be a straight line with negative slope. Okay, so you need one more point. If V input equal to, if you put 15.7 volt, you will get V output equal to 0. This is 15.7 volt. Okay, so this was the graph for active region. And in saturation region, when input voltage is greater than 15.7 volt, output is constant at 0. So after this point, we will get constant 0 voltage. Okay, this is for active region, and after this point, cutoff, and right to this point we have saturation. So in this graph, can you say that output voltage is directly proportional to input voltage? Obviously not. Okay, if output voltage was directly proportional to input voltage, you would get a straight line passing through origin, and in that case we would say that this transistor operates as, or this circuit is a linear circuit. If any circuit is a linear circuit, I would have told you while drawing transfer characteristic in Clapper circuits, if any circuit operates as a linear circuit, the graph of its output voltage versus input voltage will be a straight line passing through origin. Okay, so since this graph is not a straight line passing through origin, so we'll say that this circuit is not a linear circuit. Okay, now in the same question, I'm connecting a capacitor here. Instead of taking output here at this point, I'm first connecting a capacitor and then output is taken. Now what will be the change in the expression of output? Okay, now I have added a capacitor here. because this is the thing we are going to study in amplifier circuit. In amplifier circuit, here we will have a capacitor. So in this question only, I am connecting a capacitor, and you will see the effect of capacitor. So when we will study amplifier circuit, at this point, what is the expression of voltage? We have already found out expression of voltage at this point. These are the expression for voltage. Without capacitor, this is output voltage. Okay, and now I have added a capacitor. Okay, at this point, this is the expression of voltage with respect to ground. So you can view it as you have a source of voltage source which has magnitude given by this expression. This output voltage depends on input voltage. For different range of input voltage, this output voltage will vary, and this is with respect to ground. And I have added a capacitor here, and at this point you have to find out the output voltage, and this voltage will also be with respect to ground. So it makes a circuit. This is, let's say this is V0 dash. You have V0 dash, you have added a capacitor, and now you have to find out V0. Okay, so let us find out the output voltage for first range. When V input is less than 0.7 volt, what is output? Output is constant at 30 volt. It means when V input is less than 0.7 volt, it acts as a DC source. Here voltage is constant at 30 volt. So if you have a DC voltage and if you have a capacitor here, what will be the output voltage? Suppose you connect a resistance here. You are taking a output voltage across a resistance. Let's say we are taking output voltage across a load resistance. You have a load resistance here. Since this is also ground, so you can connect these 2 points. Okay, this is the same circuit I have drawn here. Now if you have a DC source here, in a steady state what will happen? In a steady state, capacitor will not allow any current. Current through capacitor is C dVc by dt. And for a DC circuit, the meaning of a steady state is if every quantity becomes constant. I would have discussed in network that for a DC circuit, the meaning of a steady state is if every voltage and current becomes constant. So if voltage will become constant, this will be 0. So IC will be 0. So in a steady state, capacitor will not allow any current. So in a steady state, if current is 0, the output voltage will be 0. So for first range, what we will say? For the first range, we will say for this range, V0 equal to 0. Now coming to second range. In second case, V0 dash is 31.4 minus 2V input. V0 dash is 31.4 minus 2V input. Okay. Now if you observe this part of circuit only, there is no switch connected here. If in a circuit there is no switch connected, or if in a circuit only resistance, capacitance and inductor is involved, that circuit will behave as a linear circuit. And if a circuit is a linear circuit, you can apply superposition. What is meaning of applying superposition? If you are applying superposition, it means if at input you have many voltage sources, you can find out response of individual voltage sources and then add all the responses. What we are having here, this input is composed of 2 voltage source. Okay, so what you do, find response of individual voltage sources and then add all the responses. So first we have a DC source of 31.4 volt, and you have to find out output voltage. This will be V01, and in the second case the second source is minus 2V input. This is V01, V02, and V0 will be V01 plus V02. Okay, so finding out the output voltage due to this input will be finding out response due to first input and finding out response due to second input, and then add these two responses. Now talking about the first input, this is again a constant voltage source, so this will be a DC source, and in a steady state there will be no current, so V01 equal to 0. So now can you say that how capacitor is blocking DC? In the steady state there will be no current due to this voltage source through the capacitor. So we can say that what is the role of capacitor? Capacitor blocks DC voltage. So V01 is 0. What will be the output voltage due to this source? How is this source? This source is DC or AC? Here the input voltage is a AC source. So even in steady state current can never be 0, okay, because this is an AC source, its polarity will be changing. So how we will find output voltage now? Let's say this omega is frequency of this AC source. So now we can find out the output voltage with the help of voltage division rule. We will say output voltage V02 will be minus 2V input into RL divided by RL plus 1 upon j omega c. Or if you are interested in finding out magnitude of output voltage, so what will be the magnitude? The magnitude of V02 will be minus 2V input into RL divided by root under RL square plus 1 upon omega c square. So what you observed here, what is the role of this capacitor? This capacitor will block all the DC part previous to it. What is the difference between taking output at this point and taking output at the second point? If you will take output at this point, in the output you will have AC part as well as DC part. But if you are taking output at this point, capacitor will block all the DC part. Capacitor has blocked this constant voltage. It has also blocked this constant voltage with the help of superposition. Okay, we observed that capacitor will block this voltage. So capacitor will block all the DC part and it will pass only AC part, because in case of AC we are getting some output voltage. Okay, although there will be some drop across capacitor also, but still you will get some AC voltage in the output. Okay, so we can say that capacitor will block DC and it will pass AC voltage after having some drop. Now if you want most of the AC voltage to pass through this capacitor, you want that the voltage drop, the AC voltage drop across the capacitor to be minimum. So what we will have to do, you want this voltage as close to as the V0 dash. What is V0 dash? V0 dash is nothing but, or let's say in this circuit only, let's say this is an AC signal and you want most of this voltage to drop across the load, or you want the drop across capacitor to be minimum. So this is a series circuit. current will be same for capacitor and resistance. So if the impedance of capacitor is low, there will be low voltage drop. And what is impedance of capacitor? The impedance or reactance offered by capacitor is 1 by omega c. So if 1 by omega c is less, the voltage drop across, the magnitude of voltage drop across RL will be I into RL, and magnitude of voltage drop across capacitor will be I into 1 by omega c. And if you want most of the voltage to drop across RL, you will say IRL must, this should be much greater than I into 1 by omega c, or RL must be greater than 1 by omega c. So if this is the condition, what we will say, you have capacitor will block all the DC in steady state, and if this condition is satisfied, approximately all the AC will pass through this capacitor. So, and how this condition will be satisfied? If C is large or omega is large, okay, this condition will be satisfied. So if this condition is satisfied, we can say that all the DC part of this voltage will be blocked, and all the AC, approximately all the AC will be passed through this capacitor. Okay, so now we will calculate output voltage. Okay, we have the previous output voltage given by this expression. Now after DC, after connecting capacitor, let us write down the expression for V naught. When V input is less than 0.7 volt, means cutoff, the output voltage is 30 volt DC. So this output voltage will be blocked and output voltage will be 0. When input voltage is between 0.7 to 15.7 volt, output voltage is 31.4 minus 2 V input. This DC will be blocked and you will get output as minus 2 V input. I am assuming negligible voltage drop across capacitor. I am assuming RL is much greater than 1 by omega c. Okay, and in the third case, output is 0, so the final output will also be 0. Okay, in saturation, when V input is greater than 15.7 volt, output voltage is 0. Okay, so after connecting capacitor, now let us draw the transfer characteristic of this circuit. Here we have V output with capacitor. Okay, when input is less than 0.7 volt, output is constant at 0. When input is in this range, output is minus 2 V input. We will get this type of graph. When input is less than 0.7 volt, output is constant at 0. Then when the transistor operates in active region, the output is, if you see the expression, here you have output is directly proportional to input. Okay, what I told you, transistor to operate, or for any circuit to operate as a linear circuit, the output should be directly proportional to input. It should be a straight line passing through origin. So then I told you at that time that graph should be like this. Even if the graph has negative slope, it is a straight line passing through origin and it has a negative slope. This is also a graph of linear circuit. In this case you will get negative output voltage. It does not matter. The output can be made positive just by reversing the polarity of output connection. Okay, if by taking this reference as positive, this is as negative, if you are getting negative output voltage, just make it positive and make it negative. So in this part, what you are observing, if you connected a capacitor, how is this response? If you will extend it, this will be passing through origin. So when the transistor operates in active region, and now you are removing DC parts, and if transistor is operating in active region, the graph becomes linear. This graph becomes a graph of linear circuit, or in this case, output is directly proportional to input, and this is the condition for an amplifier. Okay. When you did not connect a capacitor, the same graph is like this. When you connected a capacitor, it removed the DC part. This is the equation for 31.4 minus 2V input. So this graph is lowered by 31.4 unit. Okay. So the conclusion is, if you connected a capacitor, the region in which the transistor operates in active region, there the behavior of circuit will be as a linear circuit, and this is the condition. When a circuit behaves as a linear circuit, it can be operated as an amplifier. Here I have drawn the graph. You can also make the graph of output voltage versus input voltage. Okay, so now I will talk a little about an amplifier circuit. In amplifier circuit, at this you have an input, and here you have output, and you want output as an amplified version of input. So let's say K is gain. Okay, so you want output is equal to K into input. Okay, or output as directly proportional to input. So if you will draw the graph of output versus input, the graph will be a straight line passing through origin. Okay, so for an amplifier circuit, the necessary condition is output must be directly proportional to input. And which type of circuit will give this kind of response? If circuit behaves as a linear circuit. Okay, and in the previous question, what we have observed, when a transistor circuit operates as a linear circuit, when it operates in active region. This is the output in active region only. In saturation, the transistor circuit will not behave as linear circuit, as well as in cutoff region, the transistor circuit will not behave as a linear circuit. So if you want a transistor circuit to operate as an amplifier circuit, you have to operate that transistor circuit into active region only. Okay, so with the help of a previous example, we understood that for a transistor circuit to operate as an amplifier circuit, it has to be operated in active region. Now let's say we have an AC signal, and this has to be amplified using transistor. This is VCC, and this is AC signal. You will add a capacitor here to remove the effect of this DC, to remove all the DC part, because in the final output, what do you want? V naught must be directly proportional to V input. But if there is no capacitor, what will be output here? The output will be, if this is ground, the output will be VCC minus IC into RC. This will be VCC minus IC will be beta into IB into RC. Since input voltage is AC, so IB will obviously be AC. If IB is AC, IC will be AC. So this will be an AC signal, but there is an effect of VCC. So this effect will be taken care by this capacitor. Okay, so now we have studied that this transistor has to be operated in active region. Now if you connect a signal which is to be amplified, this is an AC signal. In the positive cycle, if it has sufficient magnitude, in the positive cycle the transistor will be out of cutoff region. So in the positive cycle it may operate in active region, but what will happen in the negative cycle? In the negative cycle, this will certainly be in cutoff region. The transistor will not be in active region, because in negative cycle current cannot flow like this. Okay, so this is not always in active region, so output will not always be directly proportional to input voltage, and this will not act as an amplifier. So to make this transistor always operate in active region, what you will do, you will connect a DC source here such that the peak of this AC signal must be less than DC voltage. Suppose you don't connect a DC source. Now what will be the expression? This open circuit voltage VOC must be greater than 0.7 volt. To take the transistor out of cutoff region, what will be VOC open circuited? If this is open circuited, this will be nothing but V input. So V input must be greater than 0.7 volt. And if this is an AC source, this will be Vm sine omega t. This must be greater than 0 volt. And since this is sinusoidal, it will become negative at some point. So when this is negative, this condition is not satisfied. So this will be in cutoff region. So the transistor will not operate as a linear circuit, and output will not be directly proportional to input. This will not act as an amplifier. Okay, so to make this transistor always operate in active region, you will connect a DC source. And what should be the magnitude of DC source? Now if you have a DC source here, now what will be the open circuit voltage here? VDC plus Vm sine omega t, and this must be always greater than 0.7 volt. So VDC must be greater than 0.7 minus Vm sine omega t. Okay, now when sine omega t is -1, VDC must be greater than 0.7 plus Vm. So what this expression tells, that the magnitude of this DC voltage source must be greater than the peak of this AC signal by 0.7 volt, because when this will be minus Vm, okay, this will try to flow current in negative direction, and here in this direction voltage has to be 0.7 volt. So VDC has to be 0.7 volt, cancelling the effect of minus Vm. So the magnitude of VDC must be at least Vm plus 0.7 volt. So if this condition is satisfied, we will say transistor will be out of cutoff region. But it does not mean the transistor will always be in active region, because it may operate in active, it may also operate in saturation region. So we have taken care of cutoff region by satisfying this condition. Now we have to take care of saturation region. Okay, So to take the transistor out of cutoff region, you will connect a DC voltage source of this magnitude, at least this magnitude. So this is called biasing of transistor, or this is called biasing. Okay. Obviously, if you are connecting this will be your input voltage, this will be bias voltage. By connecting a DC source in the output at here, there will be some effect of this VT, this DC source, but here you have capacitor, so all the effect of this VDC will be blocked, and in the output you will again get a quantity which is directly proportional to input voltage. Okay, so I'm going to give you an example in which this condition is satisfied, and in that example we will take care of this saturation region. We will let's say in this example we have 3 sin omega t, an AC signal which is an input. Although in this example this input is very high, in actual amplifier circuit the AC signal is of millivolt order, but here the purpose is different. Here I have to show you, I have to derive a condition, or I have to make you observe that when this transistor may go into saturation region. I have already connected a DC source here, a biased voltage. This is to ensure that the transistor will never go into saturation, never go into cutoff region. If you will check for open circuit voltage, when this is open circuited, there is no IE, there will be no IB, there is no voltage drop. So the open circuit voltage across transistor or across VBE open circuited, I have taught in much detail in the region of operation of a transistor, how to find out the condition to find out cutoff region, saturation region or active region. So to take this transistor out of cutoff region, VBE open circuited must be greater than 0.7 volt. And what will be VBE open circuited? This will be 5.7 volt plus 3 sin omega t. This must always be greater than 0.7 volt. Now the worst value of 3 sin omega t will be -3. So this is still 2.7 volt. Okay, this is greater than 0.7 volt. So this way I ensure that this transistor will never go into cutoff region. Now for this circuit to act as an amplifier circuit, this has to be operated only in active region. So now we have to take care of saturation region. So to operate in active region, VCE must be greater than 0. If I have taken VCE saturation equal to 0. So first we will assume this transistor to operate in active region. Okay. So first let us find out the value of IB. What will be IB? This voltage minus 0.7 divided by 50 kilo ohm. Instead of taking V input as 3 sin omega t, I am taking it as V input only. Okay, so IB will be 5.7 plus V input minus 0.7 divided by 50 milliampere. Then what will be IC? IC will be this into 100. So you will get 2 into 5 plus V input. This is IC. So now what will be VCE? 25 VCC minus IC into 2 kilo ohm. This is IC into 2. This will be 25 minus 20 minus 4V input. So VCE will be 5 minus 4V input. Okay, or instead of taking 3 sin omega t, let's say V input is Vm sin omega t. Okay, so this will be 5 minus Vm sin omega t, and this must be greater than 0 for transistor to operate in active region or this circuit to operate as a linear circuit. So if you want this expression to be always greater than 0, you will want minimum of 5 minus Vm sin omega t greater than 0. If minimum of this expression is greater than 0, then this will always be greater than 0. And what will be the minimum value of this? 5 minus, here I missed 4. The minimum value will be 5 minus 4 Vm greater than 0, or the maximum value of AC signal must be less than, or Vm must be less than 1.25 volt. And what is the Vm here? Here Vm is 3 volt. Okay, so if you are here, Vm is 3 volt, which is greater than 1.25 volt. So any AC voltage whose maximum value is greater than 1.25 volt, for that AC signal, this transistor will go to, for some time or for some duration, this transistor will go into saturation region, and this circuit will not be a linear circuit anymore. Now if you want at this voltage, for this signal, AC signal only, if you want this circuit to operate as linear circuit, what you will have to do, this is VCE and this has to be greater than 0. This is 4 minus 5 minus, or instead of 25, let's take VCC. Here I have taken VCC as 25. Let's take it as, you have to keep this quantity greater than 0, so you have to increase this 25 volt. Let's say this is VCC minus 20 minus 4 Vm sin omega t must be greater than 0. Here Vm is 3. VCC minus 20 minus, if this is 3, 12 sin omega t must be greater than 0, or minimum of this value must be greater than 0. So what is minimum of this value? VCC minus 20 minus 12. So VCC must be greater than 32 volt. Instead of 25 volt, if you put VCC greater than 32 volt, then even at this AC signal, the transistor will always be in active region. So here we observed that if you are connecting a AC signal of higher magnitude, to keep this transistor always in active region, you will have to increase this VCC. So this is possible that if you are increasing this magnitude of this signal, you increase VCC and transistor will operate in active region. But with this there is a problem. The problem is, when transistor operates in active region, this junction is reversed bias. Okay, this is forward bias, this is 0.7 volt, but this diode is, this junction is reversed bias. Okay, so now if you have connected 3 volt here, 3 sin omega t, and let's say this is 50 volt. Now what will happen? Let us try to find out the maximum negative voltage across this junction. For this value, if you will find out value of VCE, VCE will be VCC minus, VCC is 50 volt, minus 20 minus 12 sin omega t. Okay, this must be greater than 0. If you will take sin omega t as equal to 1, this will give you 50 minus 32, which is fairly greater than 0. If you will take sin omega t as minus 1, VCE will be 50 minus 20 minus 12 into minus 1. This will give you 30 plus 12, 42 volt. So the maximum value of VCE is 42 volt and the minimum value is 18 volt. Let us take VCE as, consider the maximum value of VCE. Now this is C and this is B. Okay, VCE is nothing but VCB minus VBE. I have already derived this expression. VCE will be VCB minus, no, VCB plus VBE. VCB will be VC minus VB plus VBE will be VB minus VE. So this will give you VCE. So what is the value of VCB? VCE minus VBE. VCE is, the maximum value of VCE is 42 volt and VBE is 0.7. This will give you 41.3 volt. So the reverse bias or the maximum reverse bias voltage across this junction will be 41.3 volt plus minus. Now if you will connect a higher signal, obviously you will increase this voltage also. So what will happen? Let's say at the value of 3 you are connecting 6 volt, and here let's say, because I have already shown, if you are increasing this voltage to keep out of saturation, you will have to increase this value also. If you are putting 100 volt, then what will happen? In the same expression you will find VCE as 100 minus 20 minus, here you have doubled this voltage, so instead of 12 you will have 24 here. If you will calculate from this circuit, I have erased it, but here what we have, when this was 3 we had 12 here, now we have 6, so we'll have 24 minus 24 sin omega t. The minimum value of this is 100 minus 20 minus 24, which is fairly greater than 0. And what will be the maximum value of VCE? This will be 100 minus 20 plus 24. So what we are observing here, if you are increasing the magnitude of AC signal which is to be amplified, you will have to increase this voltage, and by doing so VCE max is increasing and VCB is nothing but VCE minus 0.7. So if VCE max is increasing, VCB max, this will also increase. So by doing so, the maximum reverse bias voltage across this is increasing, and this may break at some point. This may break. Okay, so we cannot increase this voltage although if you increase this voltage, you increase this voltage also, and you will prevent this transistor from going to saturation region, but the reverse bias voltage across this junction will increase and this junction may break down. So after having so much discussion, we can conclude that a small signal AC can only be amplified. Here we can have a small signal AC. Okay. So now we have reason for connecting a bias voltage. Okay. We have reason for why this has to be a small signal. Talking about frequency of this signal, what should be the frequency? I have already showed you that we want a very less AC voltage to drop across this capacitor. Okay, for that impedance of capacitor should be low, 1 upon omega c. This should be low. So to keep it low, either you will have to increase capacitance or you need to increase omega. In the first example, what I had shown, that this voltage must be much greater than this voltage. So I showed you that I into RL must be much greater than I into 1 by omega c, or RL must be much greater than 1 by omega c. Okay. Now normally value of RL is in kilo ohm. So let's take it as 1 kilo ohm. 1000 ohm must be greater than 1 by omega c, and normal value of capacitor is in microfarad. Let's take it as 1 microfarad. So omega will be, the range for omega will be, omega must be greater than 1 upon 1000 into, it is 1 microfarad, 10 to power minus 6. So omega will be, should be greater than 10 to power 3. Okay, so if you take microfarad range and kilo ohm range of resistance and microfarad range of capacitor, the range of you have some idea about the range of frequency. So here the frequency, normal value of frequency you will get in kilohertz, from hundreds of kilohertz or tens of kilohertz to few megahertz. Okay, so this is a range of high frequency. So in the input, okay, what omega you will use here, I forgot to tell you. The omega is the frequency of input signal, and what will be the frequency of input signal here? The frequency will be same as the frequency of main input. Okay, so we have already decided this signal should be a small, okay, and frequency should be high. So we will say a small signal and here frequency should be high, but not more than megahertz, not in gigahertz, because there are other problems I will discuss in other lecture. If your frequency is in gigahertz, okay, there is capacitor which comes into picture. I will discuss these things in separate lecture. This cannot be in gigahertz. Okay, so in this lecture what we have studied so far, what is the need of biasing? We answered this question. Why this signal should be a small? Answered this question. The frequency should be in proper range. It should be in kilohertz to megahertz range. So this is answered. Why we use this capacitor? There are other capacitors also. So we will see the effect of those capacitor. But this capacitor is the most important one here to study. So what is the role of this capacitor? Okay. So now I will take an example. There will be some small signal input voltage, and that signal we will see that how that signal is amplified. Okay, let's say in this question we have to find out the value of V naught, or we have to find out the value of voltage gain V naught divided by V input. Here we have a small signal, high frequency AC signal. Okay, and the magnitude of this AC signal is such that this is much less than this biased voltage, so this will always be in active region. So if this is always in active region, what will be the value of IB? 2.7 volt plus V input minus 0.7 volt divided by 50K, or if you don't write K, this will be in milliampere. Okay, IC will be this into 100, so this will be 2 into 2 plus V input, this is AC voltage. At this point, what will be the value of V naught dash? V naught dash is nothing but VCC minus ICRC. VCC is 50 volt minus IC is 2 into 2 plus V input into RC is 1 kilo. Okay, what is the effect of this voltage source in this expression? You had 2.7 volt minus 0.7 volt, so this 2 volt, this 2 is the effect of 2.7, and here 50 is the effect of VCC. Okay, this 50 and 2. So what this expression will give you? The expression will be 50 minus 4 minus 2 V input. This will be 46 minus. Okay, this is due to VCC and this is biased voltage. So overall the DC voltage is 46 volt, and this voltage will be blocked by this capacitor. And if RL is, or 1 upon omega C is small, the AC voltage drop will be negligible and you will get output as minus 2 into V input. So what will be output divided by input? This will be minus 2. So here you will get a gain of minus 2, although this gain is very less. If you want to increase the gain, if you increase the value, this value, as let's say this is 1 kilo, you decrease this value, decrease it 10 kilo. While decreasing, if you will decrease this value, you have to take care that if you will decrease, value of IB will increase. Value of IB will be divided by 10. If IB will decrease, sorry, IB will increase. If IB will increase, IC will also increase. Okay, you have reduced it 5 times. IB will increase 5 times, so IC will also increase 5 times. So this voltage will increase. So this is also possible. If this drop increases beyond 50, you will get VCE negative. In that situation, the transistor will go into saturation. Okay, so I'm assuming that you have not increased, you have not decreased this value to a point where this transistor will go into saturation. The transistor is still in active region. So this has increased 5 times. Here also we will increase it. This will be 10. Okay, here you will get 20 minus 10 V input, so you will get it as 30 minus 10 V input, V naught dash. Okay, and V naught dash is nothing but VCE. Input is a small signal AC, so let us neglect it. So VCE is still 30 volt, okay, which is fairly greater than 0. So this will still be in active region. Okay, now this 30 volt will be filtered out with this capacitor. So now V naught dash will be minus 10 into V input, and gain will be minus 10. The voltage gain is minus 10 volt. But this is not the very popular method to find out the voltage gain of an amplifier circuit. Now from the next lecture, in the next lecture we will develop AC model of transistor. What we are doing here, we are doing DC and AC analysis in the same expression. We already know that whatever DC is coming has to be filtered out with this capacitor. Okay, so why not to do only AC analysis of this transistor? Okay, but there will be some effect of this DC, the bias voltage. So in the next lecture, first we will develop AC model of transistor, and with the help of AC model of transistor we will derive expression to calculate the voltage gain of an amplifier. And in the general amplifier circuit, we have already studied that for an amplifier, three quantities are important. The one quantity is its gain, its input impedance, and output impedance. Okay, in general amplifier circuit, we have already studied in detail. For a voltage amplifier, Z input must be large, output impedance must be low. Okay, so apart from gain of an amplifier circuit, its input impedance and output impedance are also important. So in the next lecture we will first develop an AC model of transistor. With the help of AC model, the calculation becomes easier. After finding out the AC model, we will derive expression for voltage gain, input impedance, and output impedance.